What's going on, everybody? This is Mr. Diamond, and we're going to be doing our notes over collisions today. Specifically, elastic collisions are what we're going to focus on. We'll talk about inelastic collisions in the next video. But before we do that, we've got a couple of things we'll have to talk about collisions in general. They're probably the most common type of system whenever you're doing these kinds of physics problems. During a collision, we have to do a little bit of different math. So collisions are things like, a pool ball hitting another pool ball, a car hitting another car. Those are all types of things that would be involving collisions. Same thing with most of what we've been dealing with, honestly, the rest of this chapter. In some of the example problems for the last section, there's things like a bullet passing through a block. Well, that's kind of an example of a collision. We don't really have a clear, specific definition of like a collision is when this thing occurs. We're kind of using our common sense here that it's one object impacting or hitting another object. And that is going to cause them to change their momentum and how they are currently moving. We have a whole bunch of equations we use in the first part of the year involving kinematics, but during a collision, you don't really have a way of like understanding the force from moment to moment. Like in a collision, as it is colliding, every specific instant of that collision is going to kind of have a different amount of forces at play as the energy is being transferred. It's not going to be like a linear transfer of energy. It's going to kind of vary. So just using F equals ma for a collision can be kind of tricky. But now we have two different ways to think about it. We have momentum and we have impulse. And we can use those to usually find pretty much the same types of information. Instead of having to use kinematics to find velocity and direction that it's moving, we can use our equations that we've been using this chapter. So there's two types of collisions. I mentioned one of them. We're going to be focusing mostly on elastic collisions today, but there's also inelastic. Elastic collisions are collisions where the total kinetic energy before and after the collision remains the same. So kinetic energy is conserved in an elastic collision. They're common on objects that are like really hard, they don't crumple, and when there's no heat, friction, or other energy that's likely to be produced. So in real life, not something that's usually going to happen, but like pool balls are a good example of them. Bouncing a ball off of a wall, or hitting like a bowling ball bouncing off of concrete. Those are all kinds of examples of elastic collisions. Inelastic collisions are ones where kinetic energy is not conserved. You don't get to assume that. Some or all of the kinetic energy gets turned into some other type of energy, like thermal energy or potential energy. Most real-world collisions involve at least some aspect of being inelastic, like car wrecks or throwing a ball of clay at a wall. Those are two examples that are inelastic. Car wrecks, there's a lot of energy being transferred. There's a lot of heat. There's a lot of temperature changing. There's a lot of electricity that may be being discharged in it. There's a lot of frictional energy that's going to be happening there as the metal rubs against each other. There's a whole lot of other types of forces involved. Same thing with throwing a ball of clay at a wall. If it hits and it just sticks to the wall, obviously that energy kind of got lost there. And we actually, when we talk about that later, we're going to call that a perfectly inelastic collision. Anyway, though, we're going to be focusing on elastic collisions. In elastic collisions, we know that nothing is lost to non-conservative forces. There's no friction, heat, or anything like that, which means from last chapter that our kinetic energy is also conserved. So we can set up the same type of situation. And again, this is going to be A and B are the two objects, and 1 and 2 are the two states that they're in. So the kinetic energy of thing A and thing B at position 1 should equal the same kinetic energy of thing A and thing B at state 2, so before and after the collision. But also the momentum of those two should be the same before and after. And then we can get a little creative with our math. I expanded out the equations, and if we look at it, we have our kinetic energy equation, 1/2 mv squared, and we've applied it to ma1, va1, mb1, mb, mb1, vb1. Too many letters to say too quickly. And then we expand our momentum. We have mva1, or mava1, mbvb1, and then the flip of that on the other side. Now the important piece here is, so over here we can actually combine some of our terms together, and over here we can also combine a couple of our terms. We have ma, we have ma, we have mb, we have mb, we have ma and an ma, we have mb and mb. So we can actually combine those two pieces together. So if we put together our pieces there, we will simplify. I think it actually looks, this looks scarier, but this looks more complicated. We can simplify it to ma va1 squared minus va2 squared. we get this as a simplified form, and then the other side is the same thing but with B's. This is telling you that the change, whatever change happened to the thing here over A must have been the same thing that happened to the thing over here at thing B, which makes sense. Like if you lost 100 joules of kinetic energy on the left side, it had to have been given to the 100 joules of energy on the right side. Same thing with momentum. Any momentum that was lost here also had to be the same momentum that was changed or gained over here. And then finally, we can do the thing that none of you would have just jumped to the conclusion of, which is, well, what if we divide these equations by each other? We divide the left side by VA1 minus VA2. That's going to cancel one of each of these squares and get rid of mass, cancel the mass, get rid of one of each of these squares. So we're left with, if we swap them around, because this was negative, the signs are going to get swapped, we get left with an equation that is only true in elastic collisions, but only true in elastic situations, that VA1 plus VA2 equals VB1 plus VB2. The total velocities of thing A at the beginning and the end should equal the sum of the velocities of all of the points of the system for thing B. Which makes sense. Like if thing A if it's perfectly elastic and if all the energy gets transferred, if one object is traveling at 10 meters per second and it hits another ball, if that first ball stops, we would expect, assuming they're the same size, that the ball it hits would continue at 10 meters per second because it transferred all of that energy in there, which would mean the velocity of A1 would be 10, velocity of A2 would be 0, velocity of B1 would be 0, velocity of B2 would be 10. They would be equal to each other. Again, this is only true during an elastic collision. So this equation here can only be used if it specifically tells you that the problem is elastic. Often what we're going to do for the elastic problems is solve for one variable using this. We're going to use this piece here to solve for something, and then afterwards we'll plug it into one of our equations to find an unknown variable. Usually you're going to plug it into momentum equation just because they both have the same components, but momentum doesn't involve the 1/2 or the squaring. So it's usually just easier to solve the momentum. And then in this case, like let's say you're given 3 of the speeds and 2 of the masses or something like that. You could plug in and you could say, okay, well, here's the speeds. I've solved for this piece. And then what is the masses? Well, I don't know. I can plug that in. Or if you're not given enough information in that regard, you could also be asked to, let's say you're given 2 of these velocities. You're given that this is what it was VA1 at the beginning. This is what VB2 at the end was. You can do a system of equations. You can solve for VA2 or VB1, and then you can plug that into one of these equations. And I believe that's how our example we're going to look at is going to do. It's going to be one where you have to plug it in. So the example we're going to do in a related video that'll be attached underneath this, a ball with a mass of 0.440 kilograms is moving to the east at 3.80 meters per second. It collides perfectly head-on with a 0.220 kilogram ball that is at rest. If the collision is perfectly elastic, what will the speed and direction of each ball be after the collision? So I'm going to work that out in the related video. After this, I believe the next section is going to be an elastic collision, so I think this is the last slide that I got. If you have any questions, please shoot me an email. Otherwise, this is Mr. Diamond signing off. Have a good rest of your day, everybody.